Heart disease is this massive global problem, but there's an incredible battle being won right inside our own arteries. It's all thanks to these tiny, life-saving bits of engineering called cardiac stents. Today, we're diving into some amazing research that gets into the nitty-gritty physics and science of making these devices tougher and safer than ever. And it all kicks off with one really big number. So to really get why this matters, you have to start with this number, 17.9 million. According to the World Health Organization, that's how many people died from cardiovascular diseases in just 1 year. To put that in perspective, that's nearly a third of all deaths on the entire planet. A number that big is exactly why this kind of medical innovation is so incredibly urgent. All right, so here's our game plan. First, we're going to get a handle on the medical problem itself. Then, we'll uncover this really powerful, kind of destructive force called the blood hammer effect. After that, we'll see how engineers actually built a virtual stent, put it through a seriously tough digital stress test, and finally, we'll reveal which material came out on top as the undisputed champ. Okay, so our journey starts deep inside our own bodies, with a condition that can quietly build up for years and years without you ever knowing it. The culprit has a name, atherosclerosis. Basically, you can think of it as your arteries slowly and silently getting harder and narrower. Over a long time, this gunk called plaque builds up, and it starts choking off the highway that your blood needs to travel through. This is what sets the stage for really serious stuff, like a heart attack or a stroke. And this image here, wow, it really shows you just how sneaky this whole process is. It all starts with a bad cholesterol, LDL, kind of seeping into the artery wall. So your body's emergency cleanup crew rushes in to try and fix it, but they just get totally overwhelmed and turn into these things called foam cells. Eventually, those cells create the dangerous plaque that narrows the whole artery. But here's the thing, this plaque doesn't just create a simple traffic jam. No, it unleashes something else, a brand new and dangerous problem, a physics phenomenon that, it turns out, is the absolute key to designing better stents. And that phenomenon has a pretty intense name, the blood hammer principle. Picture this. Blood is flowing along nicely in an artery, and then bam, it hits that narrow bottleneck caused by plaque. The pressure spikes like crazy. It creates this powerful, localized shockwave that puts a ton of stress on the artery wall and, more importantly for our story, on any stent that's placed there. The researchers had this perfect way of explaining it. It's just like a real hammer hitting a nail. All that force gets focused on the tiny little head of the nail. Well, that's what the artery's doing. It's focusing the blood's pressure into this intense, hammering force. Understanding that is absolutely crucial if you want to build a stent that can actually survive inside a human body. So the big question is, how on earth do you build something that can survive in that kind of extreme environment? Well, that brings us right to the core of this incredible research. This is exactly the problem a team of researchers at India's SASTRA deemed university decided to tackle head-on. And their work, with Himalatha Karnan as the corresponding author, was all about using that blood hammer idea as the key. The plan was to build a virtual model first and test for the perfect stent design before ever making a single physical one. You can see their whole game plan right here in this workflow. They started with the main problem, right? The artery clogged with plaque. Then they used the blood hammer principle to figure out the exact forces at play. From there, they did some super detailed 3D modeling, which led to intense digital simulations, all of it designed to find the one best material for the job. So they boiled it all down to 3 essential steps. Step 1 was the math, calculating the exact pressure from that blood hammer effect. Step 2 was the design, using that math to build a super precise 3D model of a stent. And finally, step 3, the test. They took that virtual model and dropped it into some powerful simulation software to basically push it to its breaking point. And get this, here are the actual models they built. All inside a computer. On the left, you can see that intricate web-like design of the stent. And then on the right, it's inside what's called a crimper. That's a virtual tool they use to simulate how the stent gets squished down and then deployed inside an artery. It's just amazing that this is all done virtually. All right, with the blueprint ready, it was time for the main event. Now they had the design, but which material could actually take the heat? It was time to run them through a virtual gauntlet. So they picked 5 contenders to go head-to-head. You've got your classic metals, stainless steel, cobalt, platinum, and chromium. And then they threw in a modern bioplastic called polylactic acid, or PLA. Each one has totally different properties, and the simulation was going to show which one was truly up for this tough job. And boom! Here are the results. This is what that virtual stress test looks like. They're applying a constant, steady force, and the colors show you where the material is under the most stress and where it's bending. What's so cool is that even if you're not an engineer, you can just see how each material reacts differently to the exact same pressure. Okay, don't let the numbers scare you. They actually tell a really cool story. You're basically looking for two things here: very little deformation, meaning it holds its shape, and manageable stress. Now, check out PLA. Its deformation is pretty low, which is great, but look at that stress value. It's absolutely massive compared to the metals. The trick is finding that perfect balance between the two. But, our hearts don't just sit there, right? They're constantly beating, they're dynamic. So the team ran another test, a transient analysis. This one simulates the pulsing, rhythmic forces of a real heartbeat over time. It's a way more realistic and way more punishing test. And it's essential for figuring out how a stent is going to perform, not just today, but for years and years to come. So after all that brutal testing, both the static and the dynamic, one material really stood out from the pack. It proved it was truly up to the challenge. And the champion, the material that came out on top after being pounded by the virtual blood hammer effect, was stainless steel. In all the simulations, it consistently showed the best all-around performance. So what made stainless steel the winner? Well, it wasn't just one thing, it was the whole package. It aced both the static and the dynamic tests. The researchers were also looking for something called a ductile material, one that can bend without snapping. And stainless steel is a perfect example. Plus, it has real-world benefits. Doctors trust it, it's easy to put in place, and it's got a long, proven track record of being safe for the human body. But really, the most important takeaway here isn't just about stainless steel. This research gives us a powerful blueprint for the future. By meshing real physics, like the blood hammer effect, with these advanced computer simulations, engineers can now design and test life-saving devices faster, more accurately, and way more safely than ever. And that, at the end of the day, means better results for patients. And all this incredible work leaves us with a really exciting question for the future. If we can design a stent for a specific physical force like this, what's next? As our tools get even better, could we move past the one-size-fits-all model? Could we one day design a stent that's perfectly personalized for your unique artery, your unique blood flow? It really feels like that's where all of this is headed.